Hello, everyone, and welcome to Lecture 6, Quantum Mechanics, Electron Configurations, and Orbital Diagrams. The first thing we're going to talk about briefly is the photoelectric effect. That is the effect that's associated with a particle that also behaves like electromagnetic radiation or has a wavelength and a frequency associated with its energy. The photoelectric effect was introduced by Albert Einstein in 1905, and this particular formula, E equals h nu, is used to describe the photoelectric effect because we're talking about a particle that also behaves with a wave-like function. That is, that particle has energy that's associated with some frequency, and that frequency is associated with some wavelength of electromagnetic radiation. The h that you see is Planck's constant, which was derived by another scientist, Maxwell Planck. What Albert Einstein realized when he was doing experimental analysis is that when he shined a light on a clean metal surface, he might be able to get electrons to eject. And so what does that mean? If he might be able to get electrons to eject, that means in some cases he wasn't able to get electrons to eject. So he was trying to figure out what is the difference between a wavelength that has enough energy to eject an electron to a higher energy level, excite that electron to a higher energy level, versus a wavelength and a frequency associated with some level of energy that will not allow it to eject. So he was altering intensities of the light, but altering intensities of the light didn't change anything. If he altered, however, the frequency of the light, that is, when he increased the frequency or decreased the frequency, he would hit certain levels of energy. So he continued to increase the frequency until he was able to eject an electron from the surface of the metal. And what he learned is that there's a threshold that's associated with ejecting an electron from a metal. That certain threshold had to be met. Any energy associated with any wavelength or frequency below that threshold would not eject the electron. But as soon as he met that threshold of energy, the electron would be ejected. Again, increasing the intensity did not affect whether or not Einstein could eject an electron from the surface of a metal, but increasing the frequency of the light did serve to meet a particular threshold of energy that would allow ejection. This meant that to scientists, to Einstein and other scientists who were looking at this work, meant that the particle, an electron, was associated with two characteristics, and de Broglie had already been looking at this. The characteristics were that an electron has particle behavior, and an electron also has electromagnetic behavior. In other words, has a wavelength, has a frequency, and has an energy associated with that wavelength and that frequency. This was being demonstrated with flame emission tests and also with gas discharge tubes. So you can see over here on the left side of the lower screen, there are some flame tests. And when you light particular elements on fire, they burn a colored glow, which is associated with the wavelength at which the electrons are residing. So when we look, for example, at this particular sample, that's methanol. Methanol burns very quickly. And so this flame has already gone out, but methanol, I can tell you, methanol and ethanol both burn white. And then next to that, we have sodium. And what you can see in sodium is this yellow-orange cap at the top, this yellow-orange light that's burning in the flame right at the top. That's an indicator of sodium. Copper gives you, as you can see, this greenish color up at the top, which is distinctive for copper. Potassium gives you this purplish blue color, and then we have a red color that you can see over here for strontium, and barium is pretty much white. a little bit of a yellowish tip burning at the barium flame. So this was one of the tests that scientists were doing, but another test that they looked at was the gas discharge tube. And with the gas discharge tube, they're showing you here by putting a CD next to a gas discharge tube that contains hydrogen gas. And what is a gas discharge tube? It has a positive charge at one end and a negative charge at the other end, and you put an electrical current through it. That electrical current will excite electrons. And those electrons that are excited will jump to a higher energy level. When they drop back down to their ground state or their original energy level, they emit light. And what you can see by the CD being put by this gas discharge tube is that it gives a line spectra. And so on both sides, you can see a line spectra. I'm just going to draw a red arrow to it here. And that line spectra has different colors that are associated with it. Well, scientists were using gas discharge tubes and prisms to show this. So here's an automatic emission spectra. What they used is a technique called spectrophotometry, and they used a spectrophotometer to show this. There's your gas discharge tube over here. And they shined the gas discharge tube, which again has an electrical charge associated with it, and some gas in it. In this particular instance, the gas isn't labeled. But they shined the light onto these slits, and what those slits did is direct the light onto this prism over here. Now this prism results in a reflection onto a detector screen. That's the black detector screen that you see here. And you can see the line spectra for this particular gas, whatever gas happens to be in that discharge tube. And you can put most any gas in that discharge tube, and you will get a unique line spectra associated with that gas specifically. And so these line spectra are unique and identifying for a given substance. They noticed patterns in these atomic line spectra that were associated with different levels of energy and different frequencies and wavelengths. So in looking at particular series, we had one scientist, Lyman, who was looking at UV rays, and UV rays are higher in energy. So here's our energy arrow increasing this direction. UV rays are higher in energy, have a shorter wavelength. So when you have higher energies, you have a shorter wavelength associated with the light. You have a higher frequency. High energy, high frequency. Shorter wavelength. When you have lower energies, lower frequency, you have longer wavelengths. So again, lower frequency and lower energy. Longer wavelength. So the ultraviolet is much stronger electromagnetic radiation compared to infrared. Then infrared is much weaker electromagnetic radiation. Paschen was the scientist who was looking at infrared, at IR, and we still use IR quite often in the organic lab to evaluate various structures. The Balmer series, though, this is the visible series. And so the reason that we're interested in CHEM100 and the Balmer series is because we can actually see the colors that are associated with the electrons dropping back down to their original energy after they've been excited to a higher energy level. And when they drop back down, they emit electromagnetic radiation in the form of visible light. And so what you need to realize here is that that visible light is going from around 350 nanometers to about 700 nanometers. And again, the longer wavelength is associated with lower energy and lower frequencies. And so we have this electromagnetic spectrum that is called Roy G. Bev, and that is that when we look at it, we see red, and then we see orange, and then we see green. So we have red, orange, yellow, that's the Roy, G, that's the green, and then Bev, blue, and violet. So those are the colors that we see, and it's a little counterintuitive because we're used to red being like a stop sign, like an urgency, and here red is actually a very long wavelength and a very low energy. The higher energy is going to be at the other end of the spectrum where violet is. Bohr's model came along in 1913. So Bohr was a scientist who was working under Rutherford in his lab. Niels Bohr was working for Ernest Rutherford, and he was doing this particular work on this atomic model in 1912 in Rutherford's lab, and he published it in 1913. Those dates I don't ask on exams. I'm just going to throw that out there. It's not that I don't want you to sit around and memorize dates, but I want you to realize that this work was all going on in the 18 and 1900s. So the 1800s and the early 1900s is when quantum mechanics came about. And Bohr was very instrumental in this quantum mechanical model, although he didn't derive the quantum mechanical model. And we'll talk about why and how he fell short on that. So what Bohr's model says is that electrons move around the nucleus in fixed paths, much like orbits that planets move around the sun. And the orbit positions are labeled with some integer n, and what they mean by integer is we could have a position where n equals 1, a position where n equals 2, a position where n equals 3, etc. And each have a specific potential energy level. So as we increase the number, we're increasing the potential energy associated with the electrons that are orbiting the nucleus at that particular n value. The lowest energy state of an atom is called the ground state. So here's Bohr's model. Let's talk a little bit about it. You've watched some videos that are going to go into a lot more detail about Bohr's model, so I'm just going to touch on it here. But the things that weren't working about Bohr's model were as follows. The model was not able to explain the spectra of atoms that had more than one electron. So the model is focused on hydrogen with only one electron. And there's only one electron, so there's only one type of orbital, and that is the s orbital that's associated with hydrogen. So the n value is equal to 1. That's the first energy level from the nucleus. So if we're talking about the nucleus being here, I'll just draw a little picture. If we're talking about the nucleus being here, and I'm just going to put a plus charge right there, then we're talking about an orbit like this, and there's one and only one electron that is traveling around that nucleus at n equals 1. So if we had more than one electron, say we had a structure that had 3 electrons or 4 electrons or 10 electrons or 20, Bohr's model didn't fit with that. Wasn't explaining anything other than a single electron at n equals 1. Other atoms have more than one type of orbital, and they have different energies that are associated with different values of n. So if you had n equals 2, that's a higher energy level than n equals 1. N equals 3 is a higher energy level than n equals 2, and so on. So the model fell short of explaining anything except for hydrogen and its one electron. And even more so, the model didn't explain the collapsing atom paradox. Classical mechanics, which came before quantum mechanics, this is Newtonian mechanics, classical mechanics. What they believed is that you could calculate any characteristics of a given function at the same time. So classical mechanics could not understand about Bohr's model why the electron didn't collapse into the nucleus, because mathematics told them that that's what would happen, that the electron would collapse into the nucleus. And when you think about it, this makes perfect sense that the electron should be collapsing into the nucleus, because if it's orbiting around a positive charge, like I've shown in that little sketch at the top, well, positive charge, negative charge attract. And so there's no reason why the electron, which is moving, wouldn't radiate and lose its energy and eventually just collapse into the positively charged nucleus that it's attracted to. And so this little diagram down here is showing you the electron is orbiting around the nucleus, but it's losing energy as it's orbiting because it's radiating that energy. As it loses more and more energy and radiates it, it's eventually going to collapse right into that positively charged nucleus that it's attracted to. So when classical mechanics scientists asked this question, Rutherford, who Bohr was working in Rutherford's lab, said the velocity balances the attractive forces, and so therefore the electron won't collapse into the positively charged nucleus. But classical mechanics didn't believe this. And the folks who were picking up quantum mechanical theories didn't believe this either. So, scientists like de Broglie, who was picking up quantum mechanics, and Heisenberg and Schrödinger, these scientists were all picking up on quantum mechanics, and they were agreeing with de Broglie that electrons had a wave-like characteristic and a particle characteristic, and this is something that had been mentioned previously that Einstein believed as well. So the quantum mechanics theories were based on the fact that there were only certain energies allowed for the electrons. In other words, if the electrons only had certain energies allowed for them, they could never get that close to the nucleus because these energies on the inside of the nucleus were not areas or regions that energy would be allowed for an electron to exist. So the electron, for example, could never enter this region. That's a region of energy that an electron cannot live in or reside in. How does quantized work then? What does quantized mean and how does it work? Because it seems so abstract to think, okay, so an electron can't reside by the nucleus. Why not? Why is that energy any different than any other energy that's there? Why can it only reside in certain distances away from the nucleus and not others? Well, let's think about this simple little diagram right here. If energy is quantized, then there's only certain discrete values that are allowed for the particle that is dwelling within that electromagnetic radiation or that energy that's associated with that frequency. The presence of discontinuities will make atomic emissions quantized. So if we look at panel A right here, this tortoise is headed down this ramp. And with that continuous ramp, that tortoise can have continuous energies that are associated with where he is at, where he is moving on that ramp at any given time. Now let's look at panel B down here and compare and contrast this a little bit. You can see that the tortoise is walking out towards the edge of a step. Now when the tortoise gets here at the edge of this step, he's going to drop to the next step. He's not going to be suspended in this region anywhere. He's going to drop straight to the next step. That is quantized energy. That means that he cannot reside, he cannot exist in a suspended state between one step and the next. He's going to drop from step to step. Again, this is exactly how an electron will behave. An electron resides at a certain energy level and not between energy levels. So here's a quick look at what Bohr's model was drawn up to look like. And you can see that we have n equals 1. And then this line is showing you n equals 2. This line, or orbit, I guess I should call it, is n equals 3. And this orbit is n equals 4. Again, Bohr did believe that electrons were orbiting around the nucleus. The fact that electrons were not orbiting around the nucleus came later with quantum mechanics. The only thing that Bohr sort of contributed to the initiation of quantum mechanics is that we did have these discrete energy levels where an electron would reside, but the electron would not reside between those energy levels. And this lined up with what Einstein said, because Einstein said you had to hit a certain threshold of energy and hit a surface of a metal with a photon of that particular threshold of energy, that frequency and that wavelength, in order to excite an electron into a higher energy level. Well, you can hit an electron with a certain amount of energy that excites it from n equals 1 to n equals 2. You could hit that electron with a certain amount of energy that would excite it from n equals 1 all the way up here to n equals 3. Or you could excite it to a higher energy level. But you notice that we never excite an electron to 1/2 of n or 1n 1/2 of n. We're always going to that full integer, to that full quanta level. And then when that electron drops back down to its ground state, because it relaxes, so it gets excited because it's hit by a photon and it jumps into a higher energy level, and then it relaxes, goes back down to its ground state, it will only travel back down to its ground state one quanta at a time. So one energy level at a time. You won't see it go 1.5 or 1 3/4 or 1.66. It's always going to drop down 1 energy level or 2 energy levels or 3 energy levels. It could drop down 4 energy levels. It just depends on how high of an energy level it jumps to. But the fact is that Bohr, and you won't have to know about these particular formulas, that we'll save for you for Chem 101, but Bohr had invested in mathematical formulas to explain these quantized absorptions of light and then emissions of light. Again, the only problem with Bohr's model is, number one, it didn't explain anything besides hydrogen, that one single electron, and that's what this diagram is showing you, one proton in the center and one electron. And that electron, according to Bohr's model, was orbiting around that positively charged nucleus. And quantum mechanics later found out that electrons do not orbit, and so we cannot know their exact location in that energy level. We can write electron configurations which list shells and subshells that contain electrons to indicate their electron population. And we can also draw orbital diagrams that represent orbitals that electrons are residing in with a circle, a box, or an underline. And we use arrows to indicate the electrons. And we also use arrows to indicate the direction of the electron's spin. Electron arrangements within atoms are placed into shells and then subshells and then orbitals. Now, you already know about the shells because we talked about them. Every element in a row or period has the same shell number. That is the same outer shell number where the valence electrons reside. We haven't talked about subshells or orbitals yet. So let's talk a little bit more about what those shells are that we mentioned, and they're numbered, and the periods are rows on the left side of the periodic table. We've seen them. So they are regions around the nucleus that contain electrons that have approximately the same amount of energy and are approximately the same distance from the nucleus. Now think about that, energy and the nucleus. And so if you are about the same distance from the nucleus, then you're going to have approximately the same energy. And remember, the nucleus is positively charged and the electrons are out here somewhere in an electron cloud. So these two electrons both have a force associated with them. It is an attractive force to the nucleus and a repulsive force to one another. That, because the distance is the same between those two electrons, and because the distance is the same for each electron with the nucleus, they will have the same energy associated with that attractive and repulsive force, and that's what we're talking about. So when you look at, for example, these two electrons, they are each in n equals 1. So they are the same distance away from the nucleus. and therefore they have the same energy, and they are in the same shell number. Their shell number is equal to 1. The electron subshells are regions within the electron shell that contain electrons that have the same energy. And we can draw electron configurations so that we can have a look at electron shells and subshells and how they relate to one another. And those electron configurations tell us the subshell occupancy. In other words, how does a subshell occupy the electrons? How does the shell and the subshell within it occupy the electrons? And then we can look at orbital diagrams, and we can evaluate the electron's location associated with the orbital. And the orbital is a region within a shell and an electron subshell where electrons with specifically energy level, where electrons with specific energy levels are most likely to be found. And we can locate them with some 90% probability, looking at probability distributions of electrons. We can draw orbital diagrams that are associated with evaluating, analyzing, or looking at where those electrons actually reside. And this tells us the orbital occupancy associated with electrons. Just to give you a little cartoon picture to get in your head how this is going to look, well, here's the nucleus that's being pointed to in here. And then we have n equals 1. And this is a region that is the same distance all the way around. This is a three-dimensional structure, as you can see, all the way surrounding around the nucleus. The electrons will reside the same distance in n equals 1. If we look at the next level for S, and this is an S orbital, and we know it is an S orbital. We'll talk a little bit more about that, but we know it's an S orbital because it's a sphere. It's spherically shaped. So next we have n equals 2. And you notice that n equals 2 is further away from the nucleus, which means it's higher energy. The reason it's higher energy is because the electrons there at n equals 2 are not as stable as the electrons at n equals 1. Remember, electrons are negatively charged. They're attracted to a positive charge. If the positive charge is closer, the negative charge is more stable. If the negative and the positive charges are further away from each other, then the charges are increasingly less and less stable. It's kind of like that child that you see in the store. At first, the child has mom on one side with one hand and dad on the other side with the other hand. And then dad wants to go look at tools or something like that, or mom wants to go get bread or milk or something like that. And the child now only has one parent associated with them, not quite as stable as they were when there were two parents sort of holding them in place. So it's similar with an electron and a proton. When they're closer together, much more stable. The further the electron gets away, the more the electron is wanting to be energetic. You can see n equals 3 here. And as we get further and further away from the nucleus, you can see that these energy levels have more space. And because they have more space, we can put more electrons in those energy levels. So let's first start by looking at the electron shells. The electron shells are designated by this numerical value, and again, that's been introduced to you when we looked at the periodic table. They are at the left side, that is 1 through 7 that we looked at. Each row or period has an energy value that's associated with it that designates the shell, the valence shell we talked about. Increasing shell number is associated with, and we just talked about this, an increasing number of electrons. Increasing space to accommodate more electrons because you get further and further away from the nucleus, and we looked at an s orbital. The sphere gets bigger and bigger as we get further and further away from the nucleus. You increase the shell number, it's associated with an increasing energy level. Again, the further the electrons, the negative charge, get away from that positive charge that holds them stable, the less stable they get and the more energetic they get. And we have an increasing distance of the electrons away from the nucleus as we increase the shell number. The number of electrons within a shell is given by this formula, 2n squared, where n is equal to the shell number. So for example, if n is equal to 1, then we have 1 squared times 2 gives us a total of 2 electrons in shell 1. We can calculate the electrons in shell 2 because we plug that 2 into this formula for n. We have 2 squared. 2 squared is equal to 4. 2 times 4 is equal to 8. So that gives us a total of 8 electrons in shell 2. Here is shell 3. That is n equals 3. So we plug that 3 into the formula for n. 3 squared is 3 times 3, which is 9. 2 times 9 is 18. So we have 18 total electrons in shell 3. And these are maximum amounts of electrons that we can put in these shells. You could have less, but these are the maximum numbers of electrons that you can put into these shells. And then if we plug 4, shell 4, that means n equals 4. We plug 4 in for n. 4 times 4 is 16, and 2 times 16 is 32. So we have a maximum of 32 electrons that can go into shell 4. So again, let's just evaluate this formula and look at this cartoon diagram about increasing numbers of electrons going into shells as the shell number increases, thereby increasing the number of energy because you're not only further away from the nucleus, but you have more electrons. And electrons repel one another. So the more of them you put together, you crunch together somewhere, the more repulsive forces you're going to have, the less stable it's going to become, and the more energy that's going to be there. So if we look at the inner shell, that is shell 1, that means n equals 1. That's what we're talking about. And we plug in 1 to that formula, then we have 1 squared, and so that is 1. So 2 times 1 equals 2, and that means that we have 2 electrons in shell 1. If we just go down here and look at the 5th shell, because that's one that we didn't look at on the previous slide. And so let's plug that in. So we have 2 times, we plug this in for n, 5 squared. 5 times 5 is 25, and 2 times 25 equals 50. And so that means in n equals 5, or the 5th shell, we can have a maximum of 50 electrons. And I'll leave the rest for you to go back and calculate because we looked at them on the previous slide. Now let's evaluate subshells. So remember, subshells are a subset within the shells. And subshells are designated by letters and the addition of letters to n, to the shell number. So the addition of these letter symbols is S, P, D, F. There's also G and more, but we're going to focus mostly in this class on S, P, and D. Each subshell contains a maximum number of electrons, and we just looked at how each shell contains a maximum number of electrons. So this is just one step further, because instead of just having the shell number, we've now added a letter symbol as well. The electrons in a given subshell contain the same energy, and the number of subshells in a particular energy level is equal to the shell number. So let's think about how this works. We look at this first example here. Shell 1 contains 1 subshell, and the subshell it contains is 1s. Remember, 1s contains 2 electrons because n is equal to 1. 1 squared is 1, and 2 times 1 gives us 2. Let's think about shell 2 now. Shell 2 contains 2 subshells. Contains 2s, that's one of its subshells, and 2p, that's its other subshell. A total of 8 electrons, because we're talking about plugging in 2 here. 2 squared is 4, and 2 times 4 equals 8. Shell 3 contains 3 subshells. Here's one of the subshells, it's 3s. Another subshell is 3p. And the third subshell is 3d. We're talking about plugging in 3 for n. 3 squared is 9, and 2 times 9 is 18. So that gives us a total of 18 electrons. Shell 4 contains 4 subshells, and you probably should be able to count them out by yourself now, but I'll still give them an underline, each one of them. There's 4s, 4p, 4d, and 4f. And we're plugging in 4 for this n value. 4 squared is 16, and 2 times 16 is 32. So there's a total of 32 electrons in shell 4, or the subshell that's associated with shell 4. Now let's talk about electron orbitals. The electron orbitals are a location within a subshell where electrons can be predictably found. Each orbital contains a maximum of 2 electrons. So this is something that you've just got to commit to memory, like the formula that was on the other page, and also the shell numbers, and also what subshell numbers are. So a 1s orbital has 2 electrons because there's only a single s orbital. 3p orbitals contain 6 electrons, 2 electrons for each p orbital. When we say 3p orbitals, this is what we mean. 1, 2, and 3. There are 3 of them. Each one has 2 electrons. Maximum. Can have less than that, but that's the maximum. 2 electrons maximum. And so that gives us a total of 6 electrons altogether. If we look at the d orbitals now, we have a look at the d orbitals, then we have a total of 5 d orbitals. If we have a total of 5 d orbitals, that means that we have this 2 electrons for each d orbital, giving us a total of 10 electrons for d orbitals. And again, that's the maximum. If we look at F, there are 7. Two electrons for each of those orbitals. That gives us a total of 2 times 7, or 14 electrons maximum in F orbitals. And if we look at the orbital shape, we've already talked about the s orbital. It's spherical. The p orbitals have 2 lobes. So some people say they're dumbbell shaped, but they have 2 lobes associated with them. I'm just going to write a p here because the writing below it is kind of small. So that's the p orbital. It's blue. It has 2 lobes. The d orbitals, that's the orange one. It has orange or red, however you want to look at that color. It has 4 lobes. And then lastly, the F orbitals. And the F orbitals are 8-lobed. And so it's like having 1 lobe going into each corner of a cube. The d orbital is like having 1 lobe going into each corner of a square. Orbitals in the same subshell have the same shape, but they differ in orientation about the nucleus. And that's what this diagram is showing you here. So the s orbital is spherical. So it's always going to have the same shape about the nucleus, with the nucleus being in the center of the sphere. The p orbitals, though, have 2 lobes, and there are 3 of them. And so there will be 1 on each axis. We'll have 1 along the x-axis, 1 along the y-axis, and 1 along the z-axis. So you can see here is the one that's on the z-axis. This one is on the y-axis, and this one is on the x-axis. Using the x, y, and z axes, we can look at the d orbitals now. What's interesting about the d orbitals, as you can see from these diagrams down here, there are some cases where the d orbitals reside between these axes. And so you can see that these sort of blue, light blue and purplish colored bubbles are residing between the axes on those two that I just put a check mark by. But over here on the left side, you can see that those portions of that orbital, because one orbital has 4 lobes, so the portions or the lobes of that orbital are actually on the axes in these two diagrams on the left side. And then this one in the center, you can see that it has energy, electron energy, that's residing around all of these axes, the X and Y axes, and then it has a lobe that is actually on the Z axes, top and bottom here. And then the F orbitals are even more complicated. Again, they can sometimes, some of the lobes will be residing between the axes while others are actually on the axes, but because we have so many more lobes associated with the F orbitals, there's always going to be at least 1 or 2 lobes that are on the axes themselves. There are rules associated with electron orbital occupancy. The electron subshells are filled in order of increasing energy. So we start at the lowest energy and then we work towards the highest energy. The electrons occupy the orbitals of a subshell such that each orbital acquires 1 electron before we start pairing any of them up. There is no more than 2 electrons existing in a given orbital. So 2 electrons, remember, is the max per orbital. And then only if they have opposite spins, and we'll be showing those opposite spins by showing an electron that has an arrow up and an arrow down. And if you want to give the arrow only one side of the arrowhead, that's fine too, as long as you show 1 up and 1 down. In the orbital diagrams, a lot of folks want to write a circle around each orbital. Some want to draw a block like that, a square around each orbital, and some want to just put a line under each orbital. And in some cases, you'll just see the arrows with no lines, no blocks, no squares, no circles. That's fine too. The electron spin is shown with the arrow up or the arrow down, and the electron spin either clockwise or counterclockwise. Why do we have to have an arrow up and an arrow down when we're showing 2 electrons in a given orbital? That's because if you push electrons that close together in one orbital, they'll keep repelling until they have opposite spins. And why is that? Because opposite spins are energetically favored. If they're both spinning in the same way, they're going to repel. We use this diagram, and this is a great diagram. This is the Aufbau diagram. And Bohr came up with this diagram. We use this diagram, and you'll see it sometimes in the videos. It's flipped 180 degrees vertically from the way that I have it. I like this diagram this way because the energy in the diagram is increasing from bottom to top. So this is potential energy. When they show it the other way, when they flip it the other direction, and the 1s, for example, is at the top and the 7s is at the bottom, then you have to realize that that potential energy arrow is going to be pointing in the other direction, and the lowest energy is at the top of the diagram, and the highest energy is at the bottom of the diagram. Because we usually draw potential energy diagrams with the lowest energy at the base of the diagram, at like the 0, 0 mark, that's why I like to draw the Aufbau diagram like this. Now you're going to have to memorize this diagram. That's the bottom line. But it's a really easy diagram to memorize. I can show you up here in the top left corner how quickly you can draw it. And so we could just say S, 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 and put, I'm sorry, 1, 2, 3, 4, 5, and 6, like this. And then we can say P, 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 and P, and we put 2, 3, 4, 5, and 6, like this. And then we'll say D, 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 and D. And here we're going to put 3, 4, 5, and 6. And then lastly, F, F, and I'm running out of room here, so I'm going to put 4 and 5. Now I want you to notice something about this diagram. it kind of rhymes, but you have SPD, and that is energy level 1, 2, 3, right? SPD 1, 2, 3 kind of rhymes. And then F subshells start on the 4th energy level. And so that's why the diagram represents that. This is a very, very fast diagram to draw. It's not hard, so don't make it harder than it actually has to be, right? So we'll use this diagram that they have over here because it's a lot neater than the sloppy one that I just drew at the top of the screen. But the fact is that when you're writing out orbital diagrams or electron configurations, this diagram will show you a smooth way to do it where the periodic table is going to have a couple glitches we're going to have to talk about on it. This diagram takes those glitches into consideration, smooths them out so you don't even have to worry about where they're at. You just follow the diagram. So I'm going to use a blue arrow just because they've been using red. And when we go through the periodic table, what we're interested in is what is the atomic number and how many electrons does a substance have? And that's how we use the off-bot diagram. So let's think for a minute about something a little bit harder than hydrogen maybe. Let's start with helium. So if we start with helium, we start at the lowest energy level, that's 1s. And we draw an arrow through 1s. And we can have a maximum of 2 electrons in 1s. And helium happens to have 2 electrons. So the electron configuration for helium, and I'll just write it down here on the bottom of the screen. The electron configuration for helium is 1s2. We use that superscript to show that we're talking about 2 electrons. If we want to draw lithium, for example, we still use the same diagram. We would go through 1s. Lithium has atomic number 3, right? We go through 1s. That gives us 2 of those 3 electrons. And we go through 2s. And remember, we said 2 electrons is the maximum for every orbital, but we can have less than that. And so we have 1 electron because lithium has atomic number 3. And so that is 1s2, 2s1 is the electron configuration for lithium. Let's think about something that's a little bit slightly more challenging. Let's go for nitrogen, for example. So if we look at nitrogen, nitrogen has atomic number 7. So I'll just write that up here in maybe a different color so we can keep track. Number 7. We said lithium is number 3, and we said helium is atomic number 2. And so now let's think about the off-bot, using the off-bot diagram to write the electron configuration for nitrogen. So we go through the 1s, just like we already have for the others. We start at the lowest energy level. That's 2 electrons. And now when we go through the next one, we're not going to have just 1 electron there because we're going to fill that one. So we go through 2s, and that's going to give us 2 electrons. So that's a total of 4 electrons so far. Nitrogen has 7. So now we're going to go through 2p and then 3s. And so that 2p that we just went through, that's going to give us 1, 2, 3 more electrons when we go through 2p, because that's all we need for nitrogen. We have 2, 4, 5, 6, and 7. So that is 1s2, 2s2, 2p3. So you can continue all the way up, and that's where they have these red arrows that are associated with this diagram. Now we could have a maximum of 6 electrons in 2p, but we didn't need it for nitrogen. Then we go back to 3s, and 3s has a maximum of 2 electrons in it. We would come back down to 3p, follow that through 4s, then to 3d, follow that through 4p, 5s, then 4d, 5p, 6s. But every time you start a new electron configuration, you're always going to start at the bottom with 1s and travel up to the top until you get through all of the electrons that you need for that particular electron configuration. When we use the periodic table, on the other hand, so we can use the Aufbau principle for any and everything on the periodic table. When we use the periodic table, it's broken up into different segments. It's broken up into 2 columns for the S block over here, the blue one. This is the S block. It's broken up into 6 columns for the P block over here, which is pink. And it's broken up into 10 columns for the D block here, which is yellow. And then 14 columns for the F block down here, which is gray. Those are showing all the sublevels. If we look at the periodic table in terms of the shell numbers, which are given here, and in terms of the S, P, D, and F blocks, now we have all of the subshells, all the shells and the subshells together, and this is how the periodic table is arranged. You can see how the Aufbau diagram showed S, P, D, and F. And remember that S started at 1. And here they're showing you S starts at 1, then goes to 2, then 3, 4, 5, 6, 7. According to the period or row numbers that we have over there on the left, those are naming the valence shells. And then if we look at P, notice that P starts at energy level 2 or shell number 2, and then goes to 3, 4, 5, 6, and 7. And if we look at D, D starts at energy level 3. So that's what we said, SPD 1, 2, 3. And then goes to 4, 5, 6. And then we have F, and remember we said F starts at 4. And so you have 4 and 5 for F. Now there's a weird glitch in the periodic table, if you can see that here. And that weird glitch is because we go from 4S over here to 3D and then back to 4P. So you notice that there's a shift in the energy level with the D block. It shifts down 1. That has to be taken care of when you're writing out orbital diagrams and electron configurations that are associated with any and all elements there. Now let's look again at the Aufbau principle. If we look at the Aufbau principle, and we'll start with the S's, and so we're going to write 1, 2, 3, 4, and we'll just go up to 5. We could go higher, but for the sake of looking at how this relates to the periodic table, we'll just go to 5. And so there's the S's, and then if we start with the P's, they start at energy level 2. So that would be 2, 3, 4, 5, and those are all P's. And then D's start at energy level 3. So 3, 4, 5, and we have D's associated with all of those. And then of course, F starts at 4. So 4F and 5F there. And let's look at how this works according to the periodic table. Let's just draw the lines through the Aufbau principle and see how it works. So we're going to go through 1S first, and that's our 1S at the very top here. So we go through 1S first, and then we go through 2S next, and that's here. And then the next thing we do is go through 2P, and then we go to 3S. So 2S, 2P, and then 3s, and I'm just putting blue check marks by them as we go through. Then 3p and 4s. So here's 3p, 4s, and then the next one on the periodic table we can see is 3d. So the question is, does our Aufbau principle take that glitch into consideration? And the answer is yes, it does. Here we go back here, 3d, 4p, and 5s is what we should be going through. So 3d, 4p, 5s. Now, does it take the next glitch into consideration, which is back to 4d? And the answer is yes, it does. 4d, 5p, 4d on the periodic table, 5p. Okay, so those glitches are all taken into consideration when we're dealing with writing any electron configuration or orbital diagram. We can use this Aufbau principle to do that. And we're going to translate. So the Aufbau principle, very straightforward, tells us how we're going to write our electron configurations in what order. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, etc. We're going to learn how to translate that to the periodic table and take into consideration its glitches. So here is a periodic table that shows you we have n equals 1. So again, over here, here are all of our shell numbers on the very left side of the periodic table. And then the energy locations that are associated with those shell numbers. And remember the little glitch that we have here at n equals 4. That is for s on this side, it is for p over on this side. But because the d block shifts down, that's going to be 3d shifting down there. So each box that's associated with your electron configuration is going to be a place for an electron to be. And we're going to read from left to right on the periodic table and from top to bottom. So let's determine the electron configurations for period 1, for example. So if we were determining the electron configuration for hydrogen, it would be 1s1. For helium, 1s2. Let's look at boron over here. So for boron, we first go through the S block, and so we have 1s2. Then we go through the second energy level, 2s2. Let me just erase this, put it somewhere else. So far we have 1s2, 2s2. Now we're over at the P block, 2p1. How many electrons does boron have? It's atomic number 5. Therefore, 5 electrons. How many electrons do we have up top in the electron configuration that we just drew? 2. Plus 2 is 4. Plus 1 is a total of 5 electrons. So here's a your turn. Which is the ground state electron configuration of fluorine? The first question we have to ask is, what is the atomic number of fluorine? Because we need to know how many electrons we're dealing with. And fluorine is atomic number 9. So we have 9 electrons to work with. We can use the off-bot principle. We could say 1, 2, 3, 4, 2, 3, 4, 3, 4. These are all S's. These are all P's. These are D's. No, she's a different color, so it doesn't blend. 1s, 2 maximum electrons, 2s, another 2 electrons, so we still have 5 to go. We can get a maximum, since P has 3 orbitals, we can get a maximum of 6 electrons in P. We don't need a total of 6. We already have 4, we only need 5, so we can put 5 electrons there. When we draw this out, we get 1s2, 2s2, 2p5. That is 2 plus 2 plus 5 gives us a total of 9 electrons. 1s2, 2s2, 2p5. That looks like C. We can draw some shortcuts for these. So those are ground state electron configurations we've been drawing, but we can draw some noble gas core electron configurations for all of the elements. So when we get bigger and bigger and bigger, we have these really, really long ground state electron configurations. We want to shorten them up. We know that every element on the periodic table strives to have the electron configuration of the Nobel gas closest to us. And that's what we can use to draw the Nobel gas core notation. So let's do that for manganese. And so if we look for manganese, it's right here on the periodic table, atomic number 25. That means we have 25 electrons to deal with here. If we back up to argon, then instead of writing out the whole electron configuration, starting with n equals 1 and going to n equals 2 and then n equals 3, we could instead just put argon in brackets. And then we know that the argon in those brackets means literally 1s2, 2s2, 2p6, 3s2, and 3p6. That's what that means. So we have written the whole electron configuration all the way through here for argon. Now we only have to write the rest of the electron configuration out in long form. So we're at 4s right here. We're at 4s2. And then we're at, remember, the D block drops 1, so we're at 3D. And that is 1, 2, 3, 4, and 5. And that is the short form, the shorthand, or the Nobel gas core notation for the electron configuration of manganese. So argon in brackets, and then 4s2, 3d5. And we skipped writing a whole bunch of electron configuration there and made it a lot easier to do. Now in the test, I'll ask you for both methods. So which of the following elements has the ground state Nobel gas configuration of neon and then 2s2? So if we go to neon, we know that we're going to back up 1. So we look at the periodic table and we say, okay, sodium happens to be atomic number 11. So we know that it's not A because we said we have neon plus this. So it can't possibly be A. So I'm just looking at B, going to B. Sodium has atomic number 11. That means it has 11 electrons associated with it. So it would be neon, which has 10 electrons. And then we would have 3s1. So it can't be sodium. Sodium cannot be neon and then 2s2. Let's look at the next one, which would be fluorine. So fluorine, neon has one more electron compared to fluorine. So fluorine would actually be, when we draw fluorine, it would actually be helium. And so fluorine has atomic number 9. Fluorine would actually be helium. And then from helium, we would have 2s2. And then 2p5 to get to fluorine. So that doesn't match what we have up there for that configuration. If we look at magnesium, magnesium's atomic number is 12. And so we back up one noble gas from magnesium, and that's neon. And then from neon, to get to magnesium, we would have 3s2. Because again, magnesium is in shell number 3. So that's 3s2. Fluorine is in shell number 2, if you look at the period or row number. Sodium is in shell 3. So you can see how our shell number that's at the left side of the periodic table is showing up in these electron configurations. And so it looks like this question with neon and then 2s2 is none of the above. It's not magnesium, because that 2 would have to be a 3 in order for that to be correct. So let's look at drawing some electron configurations of some very simple. So hydrogen has atomic number 1. That means we have 1 electron to take care of. So 1s1 gives us the 1 electron. How do we draw orbital diagrams? Now, if you've drawn the electron configuration, then you know you have only 1 electron. Remember, we said we could draw the orbital diagram by putting a line under here, or we could put a box around here if we'd rather do that. Or alternatively, you could put a circle around that if you want a circle around it. Or you could just leave it just like it is, a circle. If we look at helium, helium has atomic number 2. And so helium has 2 electrons to deal with. There's a maximum of 2 electrons per orbital. So we have 1s2. And we have to put those both in. I like to do underlines because that shows that we have an s orbital right here. And so that s orbital has 2 electrons in it. And we draw one up and we draw one down. Okay, with lithium, we know lithium is atomic number 3. And you can either use a periodic table if you have it right next to you, or off-bar. I'll just draw the off-bar diagram really quickly. Remember, P starts on energy level 2. D starts on energy level 3. And so if we need 3 electrons, then we can just draw through the Aufbau diagram. If you go through 1s, that's going to give us 2 electrons. We go through 2s, that gives us our 1 other electron. That's a total of 3. And so for lithium, that's going to be 1s2 and 2s1 is our electron configuration. We have 2 orbitals. We have the 1s, and we have the s orbital at the second energy level, n equals 2 or 2s. And then we have 2 electrons in the 1s, so we can draw that with an electron up and an electron down because they're in the same orbital. And then we have only 1 electron in the 2s orbital. Now we can look at beryllium. And so how many electrons does beryllium have? What is the atomic number for beryllium? It is atomic number 4. So there's 4 electrons that we need to take care of here. So that means we go through 1s, and that gives us 2 electrons. We go through 2s, that gives us 2 more electrons. That's our total of 4 electrons. Our electron configuration is 1s2, 2s2. And then we write our orbital diagram, which of course there's 2 orbitals. We put our electrons, 2 electrons in 1s, 2 electrons in 2s. So our electron configuration is red. Our orbital diagram has the red underlines with the black arrows that are going up and down. Those are 2 different constructs that you're going to need to be able to do for the test. Now, I know in the videos, the orbital diagrams are drawn differently. They'll draw the orbital diagrams. They look like this. So they'll have 1s and then 2s because it's a higher energy level, and then 3s and then 3p. And this is potential energy going up. And I'll do this and this and this. Sorry, it's 2s and then 2p. Let me erase that and fix it. Okay, 2s, 2p, 3s. And so they'll draw it like this, and then they'll fill it up from the bottom to the top. On a test, though, I don't expect you to do that because you don't have quite as much room. And so if we were doing beryllium, for example, on the videos, you're going to see it done like this, right? But I'm telling you to do it this way. Electron configuration and orbital diagram is on the bottom because it saves a little bit of space. Okay, so there's lithium. This is the solution. Lithium is 1s2, 2s1, and then you have 2 electrons in the 1s, 1 electron in the 2s. And then beryllium, 1s2, 2s2. There are 2 electrons in 1s. There are 2 electrons in 2s. Here's another your turn for boron and carbon. And there's the solution, and I'm going to leave these for you to draw later on. Fluorine, neon. There's the solution. And let's talk about stability and filling that outer valence octet. So that's what this diagram is showing you. It's showing you how, by filling up these outer valences that we're talking about, these elements, these atomic elements, manage to become stable. So again, everything on period or row 2, which remember, that is the shell number, that's the valence shell number, the outer shell number. Every species in that row or period is going to have its valence electrons in n equals 2, or the second energy level. And if we look at neon down here, neon has 8 electrons in N equals 2, that is its outer valence shell. So it has a perfect octet. Again, we've talked about this and we said everything on the periodic table strives to have that. And before we looked at the fact that fluorine, for example, has 9 electrons. Neon, which is the noble gas closest to it, has 10 total electrons. And we said fluorine is in group 7A and therefore has a valence of 7 electrons. And we said neon is in group 8A and therefore has a valence of 8 electrons. And now you have a model where you can really look at that valence and say, okay, now I can see fluorine has a total of 9 electrons. It has 7 in the valence, which are indicated here by red dots. And then it has 2 at N equals 1, which are indicated here by black dots. Those are called the core electrons. So there are core electrons, there are valence electrons. Fluorine just needs one more red dot, and it has the outer valence electron configuration of neon. It just needs to go from here to here, gain 1 electron. Remember, it'll have an oxidation state then of -1, and it will have the outer electron configuration of neon in its valence shell. Notice that all of the red electrons that are the valence electrons, so if we look at lithium, it's in group 1A, there's 1 red dot representing 1 valence electron. If we look at beryllium, it's in group 2A, there are 2 red dots there at N equals 2 representing the valence electrons, and we can go all the way across the periodic table looking at this, but you can see that every one of those species, and again, we're looking at the representative elements because remember the transitional elements don't always behave very well. But you can see that all of those species have their valence electrons in their outer valence shell, number 2. And they're all striving to have the electron configuration of the noble gas closest to them. Now, if lithium gives up this 1 electron that it has in its outer valence, let's talk about sort of backing up. If lithium gives this electron up right here, now it has 2 electrons, but its outer valence will be N equals 1 now, and so it will have the same electron configuration at this point as helium if it just gives up that 1 electron that has a red arrow pointing to it and a green circle around it. Beryllium could give up those 2 red electrons that have green circles around it, and then it would have the electron configuration of helium. All of these species on the periodic table are going to strive for that. Let's just look at sodium real quick. If sodium, which has atomic number 11, would just give up 1 electron, then it has the same electron configuration of neon. Let's just think about this in terms of sodium's electron configuration and orbital diagram and draw it out. And so I'll draw the Aufbau principle down here real quick so that we can use that. And sodium with 11, so we need to take care of 11 electrons. And so we go through 1s, that's 2 electrons. We go through 2s, that's 2 more electrons. We go through 2p, that's 6 electrons. So that gives us a total of 10. And we only need 1 more electron from 3s. So that gives us an electron configuration for sodium of 1s2. 2s2, 2p6, and 3s1. So there are 2, 4, 10, 11 electrons total here. And if we draw the orbital diagram, it looks like, and I'll just draw the electrons in a different color so there's a little bit of contrast here. So this is 1s2, this is 2s2, and then we have 2p, 6, and then 3s1. And you notice that if we label these, this is 1s, this is 2s, and then this is 2p, and then this one is 3s. If sodium could just give up that one electron that it has in 3s, there would be no more electrons in 3s. 3s would still reside, but it would be empty. And that would mean that sodium's outer valence shell is now 2. And how many electrons does sodium now have in the outer valence shell of 2 if it gives up that electron in 3s? It now has 2, 4, 6, 8 electrons in its outer valence shell 2, and a perfect octet that looks just like neon with 8 red electrons in its outer valence shell. If we have a look at elements 21 through 30, that is, we're going to start looking at these transition metals just a little bit. If we start looking at these transition metals, they don't behave exactly like representative metals because there is a variation associated with their ability to become stable that isn't quite as clear-cut as the representative elements are. So, for example, let's take a look at scandium, and we notice that in the outer valence shell, so here's the entire, I'm just going to put a check mark, a red check mark, here's the entire electron configuration and orbital diagram for it. But notice that we have 4s and then 3d that are being pointed out over here, 4s and 3d that are pointed out. And first, the 3d state is occupied. The valence is normally +3 because what this species is going to want to do is get the stable electron configuration of argon. Now let's think of the stable electron configuration of argon. Argon has atomic number 18. So I'll write it over here. Argon has atomic number 18. And so in order to go from 21 to 18, you've got to give up 3 electrons. So where are those 3 electrons going to come from? They're going to come from 4s first. And if they come from 4s first, then that still leaves 1 electron here in 3d. If they come out of 4s, then we could essentially have a +2 oxidation state. If we have 2 electrons out of 4s and 1 electron out of 3d, now we would have a +3 oxidation state. And so this can happen for a lot of different species. If we took just the 1 electron out, we'd end up with a +1 oxidation state. And so these transitional metals are capable of doing a lot of tricks with their electrons in their outermost valence shells. For this case, though, why would the electrons come from 4s before they would come from 3d? And the answer is because 4 is the outer valence. That's the highest in value or the highest energy level. So because that's the highest energy level, those are the most unstable electrons. So they will come out of 3D before they come out of 4S, I'm sorry, before they will come out of 3D, because the 4S electrons have more energy. They are in the highest energy level. They are the furthest away from the nucleus, the greatest distance from the nucleus. So they are the most energetic, and therefore they are the least stable. Now let's have a look at zinc, because zinc is really interesting, being the last species in the D block. So they're showing you that the transition metals, they're showing you this bracket where transition metals are from here to here. So we looked at the first transition metal over there, and now we're going to look at the last transition metal on the opposite side in the third energy level for transition metals. Remember, this is N equals 3 if we're talking about the D block. And so zinc happens to have a completely filled, so you've got 4S here, and remember, this is 4S. And then we drop back down. So this is 4S. And then we drop back down to 3 when we hit atomic number 21 and that D block. So we drop back down to N equals 3, the third energy level. But look at, for zinc, this 3D is completely filled. We have 2, 4, 6, 8, 10. So there are 5 d orbitals. Each has its maximum. And so there's a total of 10 electrons. And it turns out when you have filled or half filled, so I'm going to write filled on this one because it's filled. When you have a filled D block or half filled, and this goes for other orbitals as well, filled is very stable. And half filled is somewhat stable, not quite as stable as filled, but half filled is fairly stable as well. So when you have filled or half filled orbitals, you can count on that being pretty stable. And indeed, this is so stable that zinc always has the same oxidation state, so much so the same oxidation state that we don't even really consider zinc to be a transition metal. When we start naming, you'll see the difference. And so keep zinc in your mind when we start naming compounds, because we're not going to name zinc as though it's a transition metal. We're going to name it as though it's representative, and always, always gets a +2 oxidation state. Now, why do you think it would always have a +2 oxidation state? Where are those electrons going to come from? Since 3D is completely filled like that, we're not taking any electrons. It's going to take a huge amount of energy to get an electron out of there. So zinc is always going to be +2 because it's always going to lose those 2 electrons from 4S and not give up any, or not want to give up any at least, out of 3D, which is stable because it's filled. So let's demonstrate how sodium and chlorine, now that you have this model of electron configurations and orbital diagrams, let's use the model. And let's demonstrate how sodium and chlorine react to transfer and accept an electron, giving each a complete octet. So this is something we didn't do or couldn't really do with Lewis models. So we had the Lewis structure model, we couldn't do this. But now we have a new model that expands our ability to look at electrons and bonding interactions and be able to do this. So we draw sodium first. Sodium has atomic number 11. So we have 11 electrons that we need to deal with here. So we can use, again, an off-bod diagram. If you have a periodic table, you can use that as well. And so I'll just quickly draw a diagram down here. So this is going to be 1, 2, 3. Okay, so And I'll do a contrast color so that it shows up a little bit better. So 1s2, 2s2, 2p6, and then 3s1. So we have 2 electrons here, 2 electrons here, and then 6 electrons in p, and then we only need 1 in the other one, so that's a total of 7 electrons. 7, 8, 9, 10, 11. So we said number 11 here. 1s2, 2s2, 2p6, and 3s1. And let's just draw the orbital diagram. 1s, 2s, and then I like to draw those together. And then 3s is over here, and I'll just get a different color so there's some contrast. Here's 1s2, 2s2, 2p6, and we fill each of those 3 with 1 electron, then we backtrack and start doubling them up. And we have 1 electron here. And I want to label them. This is 1s, this is 2s, this is 2p, and this is 3s. So now let's do chlorine. So chlorine has atomic number 17. And so we'll keep going from here, and instead of 7 electrons right there, we'd actually need more. So let me erase that. So we have 1s2, 2s2, 2p6, 3s2, so that gives us a total of 8 electrons right there for 12, but we need 17, so we need 5 more. So we go to the next one, which is 3p. And we could get 6, but we don't need 6. We just need the 5 more electrons. So again, that's 1s2, 2s2, 2p6, 3s2, and 3p5. So it's 5, 6, 7, 13, 15, 17. So here's 1s, 2s, 2p, 3s, and 3p. There's our 2 electrons in 1s and our 2 in 2s. P. 3s is filled, and then we have 5. So we put 1 electron in each of those 3 p orbitals, and then we back up and put 1 more electron so that there's a single orbital that's paired, or a single part of the orbital that's paired. And now we want to look at these. So this is 1s, this is 2s, this is 2p, this is 3s, and this is 3p down here. And we ask ourselves, what do we need to do to get a perfect octet in the outer electron of both of these? Well, the outer electron shell for chlorine is 3. And chlorine right now has 2, 4, 5, 6, 2, 4, 5, 6 electrons in its outer electron shell. So I must have a mistake here. 2, 4, yeah, I need 1 more electron, right, to get 5? Yeah, I saw that, didn't you? There we go. Now we have 5 electrons, which is represented by this. I had to backtrack and fix that. Okay, so 7 total electrons in chlorine's outer valence shell of n equals 3. And if we look up here at sodium, and we looked at sodium a couple slides back, and we drew this orbital diagram, and we said if sodium just gives up this 1 electron, then it won't have any electrons in 3s anymore, meaning that its outer electron shell will now be n equals 2, and it will have 8 electrons. And so you see how sodium is going to transfer this electron here. When it transfers that electron, now chlorine has 8 electrons in its outer valence of n equals 3, and sodium has 8 electrons in its outer valence of n equals 2. And this is how they form a compound, an ionic compound, sodium chloride, where they are both giving each other a complete and stable octet in the outer valence. And this is a nicer picture of the same thing that we just went through. But I wanted you to see that you can draw this out yourself. So you can look at most any two species that are reacting together to give each other a perfect octet, either by sharing or by transferring electrons. We talked a minute ago about these filled shells, and I said that when you have these filled shells, you're very stable. It turns out that half-filled shells are also pretty stable. Not as stable as filled shells, but pretty stable. So if an electron, if an elemental atom can't get the electrons that it wants, then it can strive to have these outer filled shells or half-filled shells to gain some sort of stability that's associated with those half-filled or filled outer shells. When we look at lithium, for example, because lithium has 1 electron here in the 2s, that means that lithium is going to be really reactive. Even though 2s is half filled, it's still going to be reactive, because if lithium gives up that electron, in other words, if lithium transfers it, it now has the electron configuration of the Nobel gas helium, which has 2 outer valence electrons. And so lithium is going to be very reactive with that 1 electron. Similarly, if you look at fluorine, fluorine is going to be very reactive because fluorine need only gain 1 electron, and fluorine then, so fluorine could put an electron here, fluorine then has the same electron configuration of the Nobel gas that's closest to it, and that would be neon then. Sodium, similarly, sodium gives up this 1 electron, and sodium has the electron configuration of the Nobel gas that's closest to it, and so it's going to be very reactive to give up that electron, as we just saw with numerous diagrams. Now, there are exceptions to electron configurations that go beyond the Aufbau principle and go beyond the periodic table. So when we're looking at these particular exceptions, we look at chromium, which is atomic number 24, but it's at the top of a group, column, or family in the transitional elements. Copper is also at the top of a group, column, or family of transitional metals. And so it turns out that this whole family that has chromium at the top, or group, whatever you want to call it, and this whole family that has copper at the top of it, have this additional unexpected glitch associated with them. And they have that unexpected glitch associated with them because remember what we just said on the previous page, filled or half filled is more stable. And so if you're very close to being filled or half filled, you may make a little rearrangement so that you can become filled or half filled. How do you make that rearrangement? Well, look at chromium here. Chromium has 4 electrons in 3D and 2 electrons in 4s. Think about this. If we could transfer one of those electrons from 4s over to 3d, both 3d and 4s become half filled. And that is more stable than the situation that they currently have. So what would we see experimentally then? Well, we would probably expect to see argon and then 3d5 and 4s1. And it turns out for every other elemental atom in chromium's group, column, or family, that's what's going to happen. You're going to pass one electron from 4s to 3d. Well, you're in the next level, right below chromium, you have molybdenum, right? Molybdenum's going to do the same thing, but it's going to be passing from 5s to 4d. And then you go down one, you're going to do the same thing for every elemental atom in that family. Copper, on the other hand, is a little different. Okay, copper, having atomic number 29, has 9 electrons in 3d and 2 electrons in 4s. So if copper could just have one of these electrons from 4s passed over here to 3d, then d will be filled and s will be half filled. And so again, that is much more stable than the current situation that you have right now. Similarly, silver and gold, which are right below copper, are going to do the same thing. But gold is dealing with 4d and 5s. Sorry, silver is dealing with 4d and 5s, and gold is down one more, dealing with 5d and 6s. So they're in the same group, column, or family with copper, and they're going to behave the same way in order to fill D with 10 electrons and then half fill S with 1 electron. So what we get experimentally, this is how they determined this. They didn't just look at it and say, oh, I think they'd rather have 10 than 9, or I think they'd rather have 5 than 4. What happened is they were experimentally evaluating with electron distributions, like you'll see in the videos for quantum mechanics and Bohr's model. They were experimenting with electron distributions, and they found energy that was associated with 10 electrons at the third energy level, not 9 electrons. And they found half the energy at the 4s energy level that they expected to find, half the energy at the 5s energy level that they expected to find, and the 6s energy level. So they knew that one of the electrons was gone from the s orbital, and they knew that they had an extra electron strength going on at the d level. So they were able to show this experimentally. This is a glitch that you're going to have to remember. And really, I know that it takes a little memorization. In addition, after you've been doing chemistry for a long time, you just get it and you say, but there just is no 3d4 because it's energetically unfavorable. 3d5 is half filled, and that's energetically favorable. Or there just is no 3d9 because it's energetically unfavorable. 3d10 is favorable because it's filled. But I definitely just want to alert you, instructors love to put exceptions to the rule on exams. So you're going to see this come around when we have exam 2. This particular periodic table I like to put here because it shows you these electron configuration exceptions. And so as we said, in chromium's group, column, or family, you can see for every species in that group, column, or family that you're going to have this phenomena where we have exchanging of these electrons. And it's the same thing in every group, column, or family that's associated with copper, where again, we have this phenomena where we have this exchange in electrons so that we can fill D, you notice, and over here, we want to half fill D in every case. That is the end of lecture 6.